Maybe we should start the session 2. We'll start it with an invited talk, second invited talk of the day by Nantheera Anantrasirichai from University of Bristol. So I'll let you start.
Hi, everyone. I'm sorry I have to talk in virtually, but thank you for having me here. I am currently still a lecturer from computer science, so I probably have different knowledge from some of the audience here. My primary work is all about image and video restoration and enhancement. So then I had a good opportunity to apply computer vision knowledge to different data domain, which is InSAR, with a collaboration mainly with Professor Juliet Biggs and Dr. Fabian Albino from Earth Science and the team from COMET. InSAR is a technique using a radar signal sending from the same satellite at the same location but different time. If the ground is stable, the return signals at the time 2 should be the same as time 1. But if the ground moves, the phase of the return signals of the time 2 is different from the time 1. And then we subtract these two. And the phase difference is shown as the fringes in the interferogram images. When we unwrap the phase, and we know the wavelength of the radar signal, then we can compute how much of the ground moved in the light of sight direction between these two times. So we can use InSAR to monitor volcanoes around the world, and particularly benefit is the remote areas where the ground-based systems are not available. This world map shows the location of volcanoes acquired by Sentinel-1 satellites. They are automatically processed with LIXA, the interferogram cover 0.5 degree center at volcanoes and stored in Jasmine server. When the system fully operates, it will generate more than 1 million images per year. So clearly, automatic system to detect volcano alerts is required. Our detection starts with wrapped interferogram. The fringe lines of where the phase change between -pi to pi. And these are actually the good feature that can be used to distinguish between deformed and non-deformed ground. The concept of the InSAR technique is straightforward, but if you see from this equation that the interference that causes the automatic system is like not perfect. So the main issue is water vapor that could appear in interferograms that look like many fringes as well, like shown here. So the top row are the real deformation signals, but the bottom row are atmospheric effects. So here we want to classify the deformation from other signals like background and noise and atmosphere, like you see the equation that's shown in previous slides. And this is the diagram of the deformation detection. So the top part is the training process where we use synthetic examples to train the classifier. We define this problem as the binary classification. The training data set, the positive samples are the image that contain deformation signals combined with stratified and turbulent atmosphere. The negatives are the combinations of the atmosphere only. So we employ the convolutional neural network or CNN to classify these two signals. After training, we use the model to run detection, and then the expert checks. And the false results, like false positive and false negative, are used with the synthetic sample to retrain the model. Just a bit of recap of how CNN works. It captures spatial relationship among neighboring pixels through convolution operation, as its name actually is correlation. Like you can see in this animation that how it's like a filter that with 3x3 in this one. The CNNs automatically extract features from the low level, like the lines and blob, and then connect them to the next level, like line connect to the line to the triangle, for example, to the higher level that contain semantic meanings. So filters in each convolution layers are learned from the trained data to match the input image to the output result, which is here produce the probabilities of being each object. We didn't train CNN from scratch, but we used the pre-trained network and fine-tuning them to learn characteristics, in particular for InSAR images. And when we started, we tested several networks and found that the shallower architectures like AlexNet give the better results than the deeper one. So we used AlexNet. You'll probably consider why, because a lot of the network that proposed out here is for object detections, and most of them detect like thousands of objects. Like it also contains so many different shape and stuff like houses, horse, cat, plane. But in this particular work, we only detect the fringes. That's why narrower is better, because it not confuse the network. We don't need the high nonlinearity of the data set as others. The simple deep learning framework is, however, quite like we need good balance between the positive and negative samples, because otherwise, when we train it, the model will bias to the majority class. And this becomes the real problem for the volcanic deformation detection, because the real positive signals are very rare. As you can see, the statistic that I show here is only 0.15% for the whole data set that actually is deformed. So when we first start our project about like 5 years ago, we have only the NVSet data set. So we use that, the simple technique called data augmentation to balance data set. So the positive samples are augmented with rotation, flips, distortion, and translation, while the negative samples are select only where the patch that contain the age of that. But because we use the wrap interferograms, of course, if the path doesn't have any age information, that means it's no deformation signal. Then we improve our dataset with the synthetic components using multilateral approach to select the source parameters and project the 3D surface displacement into the satellite line of sight. We use the deformation model, Okada, Moji, and Bianco, and we obtain the stratified atmospheric component from the generic atmospheric collection online server we call Argos. We use 100 Argos stratific delay and maps to the with about 12 days interval, which is exactly the same as the Sentinel one. And the last component is the turbulent atmospheric delay, which are spatially correlated, and their correlation can be described using the exponential decay function. And the final sample that we use for training will combine all of them together. After we obtain the model, so we use it in the prediction process, which is the bottom half of this diagram. The prediction process is that the neuter program or InSAR image is divided into overlapping patches. So each patch is the same size of the input of the AlexNet required. Each patch is tested by the trained CNN, giving the probability of being deformation. So there's only one value per patch. And then in order to get the whole thing, so the probability is that it merged with the Gaussian weights to create the probability map of the input interferogram. Then the local maxima is detected, giving the final results. And you can check my code in the GitHub that provide here. Now I show you some results. Each pair is the interferogram and probability map. The brighter yellow is the higher probability of being deformation. There are some false positives like island or the strong atmosphere here. After the expert checked, so we fed the predicted positives to retrain the network again. And we found that it reduced the number of false positives significantly because now the network or the model already learned the characteristics of the satellite images, particularly in Sentinel-1 interferograms. However, you can see here there's still one false positive that are missed, which is this false negative here. It didn't happen where the interferogram show only one fringe, because the CNN learned the fringes. So when only one fringe, it cannot see the pattern very well. So you can see like here, it's a time interval with only 12 days. So more fringes show in the longer time spans, like the top and the bottom ones. This also implies that if volcanoes are moving very slow, the number of fringes is too few that have shown in the interferogram. So the current CNN cannot detect them. From the plot on the right-hand side, most volcanoes, however, are moving at slow rate. So they are below the threshold of detection, like below the green line that's seen in this plot. To overcome the slow deformation, we proposed rewrapping techniques to increase the number of fringes. Here, 5 represent the phase, and then we multiply this phase with some gains and rewrapped it back to -pi to pi. So the left column of this is the original wrap interferogram with different level of noise. So the higher noise means it's more difficult to detect the deformation signal. So then when some gains are applied, the signal have more fringes. However, if you rewrapping too many times, the CNN could be confused because of the noise start having small fringes too. As you can see from the bottom right image, the probability is dropped. So we propose using the average of the probability of 4 gains. So we use the gain is 1, 2, 4, and 8 here. So this show an example of the case study in Italy. First of all, in order to obtain we use the cumulative time series. So if you add it more, so then you can have the longer time span, as I mentioned before, longer time span, meaning you can have more fringes as possible. So we process Sentinel-1 SAR images using RIKEN system, which generates automatically with 3 short duration interferograms for each time acquisition, like 6, 12, and 18 days. The interferogram are not corrected from the atmospheric signal here. Linearly square inversion is performed on the network for unwrapped interferogram to obtain the time series of the cumulative graph deformation using the single value decomposition and assume no deformation at the first date. This is in the case study in Italy, you can see all this plot, the vertical red dot line. So each plot is where the uplift start, which is about July 2017 in area B. The area A is stable. So no surprise that the probability from area is almost 0, while the probability from 4 gains shows some deformation detection that you see in the middle row. You can see there are some false negatives when using the gain of 1. So detection is delayed about like 8 months from the onset. So when the gain is increased, the probability of finding the deformation is also increased. And when the gain is the highest, which is 8 here. Some false positives are generated. As you see, the first half before the onset of July 2017. So then we then get the final result, as you see in the bottom plot, that we get the averaging of the result from all gains that applied. So if we flag the deformation at a probability more than 0.5, now the detection is found about 2 months after the onset instead of 7 months as shown in the first one. Now, the detection threshold is reduced, and we use this new method to find the volcanic deformation around the globe. Okay, this is the global results from the automated system with the signal detection. At 15 April last year, there are about more than 640,000 RAP interferograms of the 1,098 volcanoes. So the world map shows spatial distribution of detections. The sites, the circle side represent the number of detection, and the color represent the percentage of detections. And the histogram B, bottom left, shows number of detection per volcanoes, and the histogram C shows percentage of detection per volcano. More than 35% are from volcano at Galapagos Island. The histogram showing the number of the positive per volcano and found detection most at the Sierra Negra. For the following is the Fujisan in Japan. So we actually analyzed it by applying the atmospheric correction using dark cost with a model, and found most of detection at Fujisan are false positives. But other volcanoes like Fernandina, Moya, Wolf, and other labeled here are true positives. At least, so this framework reduced the number of the interferogram for expert check by down to about only 0.55% of the whole interferogram that have. And the probability can be used to rank the priority for the inspection, as you can see that we show in the histogram here. You may explore machine learning to implement it on the Jasmine at Comet portal link addressed here. Before moving to the UK case study, I would like to mention about atmospheric collection. So the process improves the detection performance when unwrapped interferogram is available. So remember the thing that proposed is for wrapped interferogram, but if unwrapped is available, so we can apply some the weather model. The traditional way is using the weather model. We employ Garkos technique that calculate to delay difference and subtract the atmospheric effect from the histograms. So you can see from the result here that the atmospheric correction can reduce some false positives, but the process of using weather model could be quite slow. And so then we try machine learning. So we adapt the idea of removing noise in the natural image to remove the atmospheric effects in InSAR data. For example, here using the DN-CNN, which is the denoising that applied for the Gaussian noise. The network estimates the noise map as the output. In InSAR, though, the atmospheric signal are not Gaussian distribution, so we remove the batch normalization and train the network with synthetic data set, which is done by the my master students. The same set we use the data set, we use the same set to train the ElecNet deformation detection. This shows some results. We test the detection before and after atmospheric removal with the DN-CNN. The false positive rate is significantly improved. So next, I'd like to present our work so the extent from the volcanic detection to detect the ground deformation in the built environment using InSAR data. So this is quite different now, as you can see from the data, because they're quite a different process for InSAR. So in the volcano case, you will have stratified ones, so you get dense data, but in the built environment, you use different techniques. So you can see the signal that you want to detect the ground deformation is like velocity map in the London here. The data are sparse. So there are gaps between pixels, which is not suitable for CNN anymore. Moreover, as it used different techniques to acquire InSAR, the data contains spiky noise. So we are also facing other problems. We don't have good label data, and what we want to detect appear to be slow and localized. So we tackle these problems with 3 proposed techniques merged together. So spatial interpolation to deal with the sparsity. We're using synthetic data to train and apply overlapping or rewrapping techniques to detect slow motion. For spatial interpolation, so we apply the technique called metric completion to where the InSAR. So this service like before, because it's sparse, so it's not suitable for AlexNet. So metric completion see these as the inverse problems and try to solve it with the regularization approach using the singular value decomposition. This is an example of the result. So the top left is the raw sparse data containing spiky noise. The bottom left is the interpolated result using traditional triangular method. It enhanced spiky noise compared to our method on the bottom right, which is smoother. So then when you wrapped it again, so this will show clearer result that's suitable for to be used by CNN. So the outcome from the AlexNet with the sliding window is shown in the top right figures, that where we detect where the ground is deformed. I also would like to, it is like there is an extra slide, so I would like to try, so we try the deep learning, what happened if we use deep learning to do the spatial interpolation and simultaneously upon denoising. And this is called self-supervised learning. It makes use of the CNN as well to enhance the giving image with no prior training data. So other than the image itself, so the feed image in, and the input is that, so you can say, for example, the random noise, and then the network learn the statistic of giving the image to L1 and L2 loss functions. So basically the output of the network is compared to the given image, which is the raw data. So in the InSAR case, the loss function is calculated only with the existing pixels, and the spatial correlation and the prior are learned through the convolutional image generator. The final result here, we marked out where the area is too sparse, because compared to the metric completion method, the deep learning, this like for self-supervised learning is significantly faster, but it won't work at the area that the data is too sparse, because they have not have enough data point to learn. That's the problem. However, it very fast, very nice, and this is still more investigate more to get the better performance on this. So now we run the detection method on the whole UK data from substance, which is 10-meter velocity maps. There are more than 90 million data points, which is more than about more than 3,250 full HD TVs combined. So to automatically process this large velocity map, so we divide it into several 2,500 by 2,500 maps. Sorry. Okay, so well, the figures show the center of the location where and detect them as the being deformation. So the result show here is the coal mining region in the area, the A to F, around the Midland of UK. In the northwest of Wales, is the detect subsidence from the foremost lake quarry, and the area G shows the uplift of the the groundwater rebound after the construction of the cross rail finished. So from the histogram in previous slide, so we set 3 thresholds like 5, 45, and 5 millimeter per year to classify slow, medium, and fast deformation to apply the threshold technique. Comparing with the proposed method, the threshold technique generates significantly more positive points for experts to further investigate. So CNN detect 258 sites, while thresholding method detect more than 4,000 positives. So there is, however, limitation using CNN alone. For example, landslides with significant horizontal motion were detect in the south of the Kirby Stephen, but the method didn't detect in the other black veins on the west of Dorset. And not surprised, the sinkhole problems that cannot be detected at all because it's only one pixel that moves. So to overcome this, another thing that we are developing is using the spatial temporal or 3D analysis of InSAR data, see at the volume, so then we can get the time series in as well for future work. Okay, to wrap up, so I present you the deep learning framework that automatically research for the last volume of InSAR that detected the rapid ground deformation, and we overcome the imbalance data set with synthetic example to get more generalization of the model. We usually use the simple the models, AlexNet, which is the most suitable for these problems, and slow motion, slow deformation are detected using the cumulative signal, sometimes in overlapping signal. And then we adapted it to the built environment, and that I showed you before that more suitable, but we need to apply some spatial interpolation so that the data are suitable to apply with the existing CNN. Thank you. Any question, I'm more than welcome.
So we have time for a few questions. Anybody has a question they want to ask now? So you mentioned that AlexNet was the best in this task because it was the simplest. So did you try some simpler techniques even yet to regularize better?
What we try is actually we tried quite a lot of the models, and we found that the AlexNet extract the rapid features the best. But the main purpose of the project is to do machine learning, which is deep learning here. So I actually never try other simple, like using image processing alone, say, or SVM. But I imagine that because we
or even just earlier layers of AlexNet.
We first try, like say, like only a few layers, like 3 layers, right? When we try that, but when we start, however, the data set is not very large, and we want to use pre-trained network. That's why I show you only the model that already pre-trained or other people used, instead of try to create our new architectures.
Question over here from.
Thank you for a very nice presentation. I'm wondering about, again, come back to landslide. What you did there, it was landslide detection. Did you use like sentinel data for detecting landslides? In one slide, I saw 2 locations in Britain.
You mean here, landslide?
Yes.
So, so the model that we train for so general. So yes, we include the synthetic data sets that the expert tell me that it's model for the landslide, for the other subsidence or anything else. So we train everything all together. However, because the landslide is very small, so if the landslide is big enough to have fringes in the image, so the CNN no problem to detect it. But if you see from the lower one, the signal sparser, and also the size itself is quite small. So the CNN won't work for only a few pixels because the CNN itself is, as I said, it to detect the spatial correlation between pixels. If pixels don't show any fringes, so CNN cannot detect. So that's why the further work now that students doing is developing the 3D CNN. So then we can learn to get more data points from the time series. Yeah.
Okay, thank you. I'm asking because 2 years ago, I was trying to detect landslides in higher Himalaya. And with Sentinel-1 data, radar data, I tried a lot, but I couldn't, because of two reasons. I see one is the resolution of Sentinel that you also mentioned because of the size of landslides, and also the high slope that we have in Himalayas. It was like the features that you extracted from CNN, from Sentinel-1, I don't know, the different things we use into program 3 or land deformation. They were not very useful to detect exactly the landslides. Okay, have these results published somewhere?
We detected we report as the whole UK, so include all the models. But we have students now also working on the get the subset on the railway network and also the highway, which is probably quite similar to the landslide in terms of the data array sparse and it's very small pixel. So we try to come up with the other using the image processing technique, which is also associated to the deep learning, and using to learn as they try to get the patterns in such a way that associate to the line of sight left and right to see if we can combine between the descending and the descendings, because when the line of sight is different, so the landslide will show the different characteristics between these two. And if we manage to merge between two different angles and we work together and somehow concatenate, for example, that fit into the network.
Yeah, exactly. This is another problem that I forgot to mention, that the aspect of slope for descending and ascending is also. Yeah, thank you.
I do have a question because I'm not actually familiar with this area, but you were showing these overwrapped images by multiplying the phase with the gains, right? And it sounded like you were using these overwrapped images as inputs to the same network, to the same prediction process, and then averaging probabilities. So have you thought about actually just concatenating those images into a feature vector and training the network from there?
We actually try both, but the result is not significantly different. I do understand that because when you rewrap this, the signal to noise ratio is not actually much different, and the network also sort of when you rewrap more, right? So these already actually show in some of other data set in somewhere else around the world. So we use a global data set, right? So it probably happened that it shows some in some of the synthetic data set that we produce. So what I'm trying to say is that it's already included in the training data set. But is it for training? Yes, for when you detect it. it doesn't seem to show. That's why we try to come up with the better way to get more features that the network they already learned. Yeah, with more confidence. Say, yeah.
Well, thank you. Let's thank Hui again. And next we have Agatha Mattos.
Good afternoon, everyone. My name is Agatha, and I'm going to present to you today the work I did with 2 other collaborators on mapping slums with deep learning feature extraction. So slums, according to the United Nations Habitat, are locations where residents lack at least one of the following: water, access to water, sanitation, housing durability, secure tenure, or sufficient living area. Now, there are many reasons why we would be interested in mapping the population, the location of slums and the population living there, but one of them is that goal 11.1 of the Sustainable Development Goals say that by 2030, these communities should be upgraded. At the moment, it is estimated that 1 billion people live in slums around the world. That's roughly like 1 in 8 of us. But this data comes mostly from census surveys, which are not carried out in frequently enough to keep pace with the changes in these communities. So for that reason, we are looking for alternative ways to do this. Now, when you look at slums from above, they can be quite distinctive from the neighboring areas. And for this reason, we would believe that like Earth observation and satellite imagery would be like good candidates for like estimating the population living in slums and mapping these communities. However, despite the increased number of satellites in orbit and the advances in deep learning, mapping slums worldwide is still like a challenge. Now, there's a few reasons for that. And one of them is, like as other people mentioned today, the lack of ground truth data to train supervised models. And also the like, even when so this is an example of an area and the ground truth data. And also when we have models, they don't tend to generalize well, given the diversity of slums across the globe. Now, another challenge related to mapping slums has to do with the cost of acquiring and pre-processing satellite imagery for large areas. That's especially true if you're working with high resolution imagery, which often has to be acquired. And to date, most of the approaches that exist in the literature use very high resolution imagery. Now, another challenge has to do with the fact that, as again, like common in this kind of problems, that like it's a very imbalanced problem. So like slums usually represent only a very small fraction of the total image. You see here, these are the 2 locations that we studied in the work that I'm presenting today. So in order to tackle these challenges that I've just mentioned, in this work, we investigate an unsupervised method to map slums. So we employed 3D available medium resolution satellite imagery. Also, the method does not require label data. And it is cost efficient because it's using medium resolution imagery, and also like only a fraction of the whole image was used to train the model. And then we compare the results of our method with a supervised learning model. Now I'm going to explain first what is our baseline. So what's the method that we are comparing our unsupervised approach to. So it all starts with like the satellite imagery of an area. There in red are actually the slums for this location. Then we tile this image in like tiles of like 20 by 20 pixels. And using the ground truth data, we label the tiles that have more than 50% of the pixels as marked as slums in the ground truth. They were considered like slum tiles. And then we used 20% of the slum tiles to train the model, plus 4 times this amount of tiles of like non-slum tiles that were randomly sampled from the whole image. Now, with this data, we fine-tuned a ResNet 18 model that was initially trained with ImageNet images, and we evaluate the results using intersection over union. Now, the unsupervised method that we propose, it is to a certain extent similar to the baseline, but it differs in the fact that it doesn't use labels, and as well, it doesn't use any of the labels of the ground truths. So like basically each tile is put into like ResNet 18 network, and then the output for each tile is like a vector with 1,000 rows, which we then subsequently use to cluster the remaining of the data into 17 clusters. Then because we didn't want to rely on visual inspection to decide which clusters would be slums, we leveraged this other data set that actually has the complexity scores for most of the areas of each of the 2 towns that we studied. So basically, this complexity score is the data set that uses information from OpenStreetMap for those areas. And it gives a score that goes from 0 to 20, and lower score values represent less developed areas. So because we have the 17 clusters, we calculated the average score for each of the tiles in the 17 clusters. And then we come up with the median complexity score for each cluster. And then the clusters that had the lowest complexity score were assigned as slum clusters. And then we use that to cross-check how good this model was, the unsupervised model was, to actually separate the slums from the non-slums. And then the results show that the supervised method on average performed better. The supervised method actually performed better than the unsupervised method. And in the future, we want to try new strategies for dealing with the class imbalance and also assigning the slum clusters. And as well, we also noticed that the intersection of a union that we obtain using medium resolution data, it is kind of comparable to the results that were obtained in the literature using high-res imagery. Thank you very much.
So these are short sessions. Yeah. And the next talk is by Elena Rosa on optical Weak-supervision based on label proportions for Earth observations.
Hi everyone, my name is Elena. I'm a PhD student at Pontifical Catholic University of Rio de Janeiro, and also I'm a PhD guest at HZDR under the guidance of Professor Pedro Angamici. Today I'm presenting our work entitled Weak Supervision based on label proportions for air observation applications from optical and hyperspectral imagery. The use of prior to avoid manual labeling has arose recently as a powerful tool to alleviate the burden of manually annotate data that is highly, it costs a lot of money and you need expert knowledge, mainly for air observation data, when the experts need to have a large amount of study about certain applications like agriculture, forestry, and so on. Considering this learning from label proportion, that is when you only have information about the proportion of the labels in your data, but you don't know what is the label of each pixel of your image. You only know that you have certain amount of samples from one class and certain amount of samples for the other classes, for example. And this weak supervision approach has been used in the last years for many applications, ranging from governmental elections, healthcare system, image classification, and so on. And this group of labels, these proportions can be obtained from governmental census. For example, we have in many countries governmental agencies that they have statistic information about the proportions of certain, for example, agricultural crops. In Brazil, for example, we have a governmental website with the amount of the proportion of the soybeans or cotton or maize that are the crops that the government is interested on for exporting and for the economical development of the country. And in other countries, like here in Europe, we have other agencies that monitor different kind of information from forestry to agriculture. And we use this information that is just global. We don't need to annotate. We don't need to spend time and money in looking in the image what we have and try to have a dense annotation. If we use this information, we can have an important impact in real life application, principally for air observation applications. And considering this, this work will focus principally in crop mapping and geological mapping that are two different applications. And because we want to access or look the potential of this application of learning from proportions for two different tasks, very different tasks, and they are crucial for the environmental impact we already have in our planet. Considering this, we are using a state-of-the-art technique based on self-supervised learning, specifically contrastive learning methods, that basically these methods propose to apply different augmentations to an input image and try to apply a loss function that is going to compare the augmentation of this image and try to increase the similarity between augmentation of the same image and increase the dissimilarity between augmentations of different images. And this way, we are learning helpful, important attributes in a fully unsupervised way. In this case, self-supervised, but we don't need labels. Combining this self-supervised approach with a cluster or class proportions, recently this a paper was proposed, a method called learning from labels proportion with prototypical contrastive clustering. And this is a method that combines the self-supervised learning with learning from proportions using an optimal transport theory. And basically, what you can see in the image is the proposed approach. You have input images, and we are going to apply different transformations to each one of these images. And the objective is to assign the images to each one of the clusters. We need to predefine this cluster, knowing how many classes we have and what are the proportion of these classes. We can train this classifier that at inference time, we only need to fit the input image and look at what of the cluster where I assign this, where this image assigned. And that way we can know, for example, because we know that the cluster that have 35% of samples are the cluster that deer, and the cluster that have 15% of samples are the cluster that pertains to dog, and so on. We can just using the global information, we can train a classifier that is going to assign a class for each input image. Now looking at the remote sensing application or air observation application, this is how we adapt this method to our application. Basically, we have a large scale input image. Then we crop small patches or tiles. And we basically want to assign one of these tiles to each one of the clusters according to the constraint imposed by the proportions of the cluster. To access our method, we select two different data sets from two very different applications and with different sensor type. we have an agricultural data set called Campo Verde. It's an agricultural data set from Brazil, and it contains around 14 classes, but the most important ones are cotton and maize. And we also have a second data set about geological mapping that is located in Spain. It's an open pit mine, sorry. And the most important minerals we have, we can group these minerals in chloride and mineralized volcano. Then for our approach, we focus on the major classes, the most important ones. For the agricultural data set, cotton and maize, and for the geological mapping, are these classes that I just mentioned, and the rest of the classes of the data set are grouped in a class called others. Our results, we can see the performance in looking at the overall accuracy and the F1 score, and also the clustering metric. We can observe how the approach report very high accuracy, about 91% for both data sets. The F1 score is a little bit lower in the geological data set because we are talking about, I forgot to tell, the crop type data set use optical images and the geological data set use hyperspectral images. Then, because we are working with hyperspectral images to try to separate this kind of different minerals from the data set, this is a most challenging task that just use optical images to classify crops. That's why we have 76% of F1 score for the geological data set. And we also report the confusion matrices. You can see how for the important classes, the ones that we are interested in are, we have about 91% for both data sets. And for the geological mapping, we have that the class more challenging was the class others, because it contains a large amount of different type of classes that are mostly vegetation and water minerals. But the classes we are more interested in, we have a very good performance, considering that we are only using the proportions of the class we have in the data set. And finally, I want to show just a clip of the prediction maps compared with the self-supervised method that we use as baseline that doesn't employ proportion information about the classes. And we can see that the mapping are kind of accurate, except some regions, for example, the other class others in the geological data set. Where this work shows access a recently proposed weak-supervised method that uses class proportions to train a classifier. We employ this method for air observation applications. The method was capable of achieve reasonable good performance, good accuracy values, proving being robust to different data sources and different applications. And the overall accuracy was about 99%, 19%, and the approach also failed to classify classes with very small proportion. This class is the other class, for example, that have very small, like 10% of the samples were only for the class others, and that's why we also, the model struggled to identify this class for the geological data set. Thank you very much for your attention.
The next talk is by Bruno Adriano.
Hello, my name is Bruno Adriano. This work is mainly done by Johnson. He's a PhD student at the University of Tokyo, supervised by Professor Nantheera. I'm just representing the work of this student. So his work is in disaster detection from SAR images with different off-nadir angle using unsupervised image translation. Okay, I think we all agree or we all understand that in some applications, SAR or radar data, especially synthetic aperture radar, SAR has some advantage. For instance, this is a possible data from Sentinel-2 after the Typhoon Hagibis in Japan. And you can see that there is a city there, but this is covered by cloud, right? We cannot use optical data for flood detection in this case. So in such scenarios, SAR dataset gives us great advantage. We already understand why the active sample is very useful. And here you can see the flooded areas is mainly the dark areas, right? And I think there is many work for flood detection or land or affect flooded areas using SAR dataset, either post-event only, I mean only one scene, or using multi-temporal change detection analysis in one scene from before the disaster, pre-event, or post-event. So for instance, here is a quick example of combining a simple combination one scene before and after the disaster, and one RGB color composite. See the red area, red segments are the areas that are flooded in the paddy fields, and some blue areas, bluish areas is the flooded area in the city. Okay, so we can do this because the pre and post SAR scenes have almost same acquisition condition. That means same orbit direction and same off-nadir angle, or same angle, the same angle respect to the vertical. Okay, but what happened we don't have those images. So what happened when the pre-event and the post-event have different satellite path direction or even different angle observation, off-nadir angle. So we cannot do change detection, or we cannot do some other simpler techniques that allow us when we have same acquisition condition. So that is the problem that we want to solve here. How doing flood detection with different condition of pre and post event data sets. So for this case, the student proposed two methods. This is just using already proposed architecture. The first one is using CGAN, a Untitled network. So in this case, we trained the GAN to reproduce post-event using pre-event information in areas that doesn't have any changes, any disaster information, let's say. And we use the trained network to produce the post-event corresponding scene when there is some flooding. And then we just use some simple change detection analysis in this part. In the second part, code alignment autoencoders is a little bit much, let's say, elaborate. But it's based on the paper below. And here we train two architectures, two encoders, and both try to reproduce post-event from the pre-event, but in one in case there is changes and one there is no changes. So the trick here that we swap or we switch the decoders and based on the loss function proposed in this paper, this switching tries to force the network, force the architecture to reproduce areas that have no changes. So we can, how to say, once we apply this, we can detect the areas that have changes, which in our case is the flooded areas. Okay, so this is the methodology. This is in our paper. You have a question, please, or we can chat later. So I will go to the results. So from your left, we have the pre-event image with the incident angle here is 25.6 degrees, and we have the post-event image. They look different, of course, because they're different. There is the disaster, also the incident angle is totally different, right? That is 5 degrees. So in the next one, the third column image, we have simple image analysis thresholding using pre and post event with the same acquisition parameters, same incident angle, same path. Okay, this is kind of the standard way, very easy to detect. Just we don't need much. Probably we don't need to use machine learning. Just simple image analysis change detection. We can get this is a f-score of 0.65. Okay, so the next one is using the same technique, change detection, but using the image in the first and the second column. So chain rotation, we shouldn't do, right? With the image, the image angles are different. So this is and then we have our result with using the CGAN, and it's better than the standard change rotation analysis. We have the CCA method, it's lower. And also, I forgot to mention, for this case, we also, before entering into the architecture, we do some modulation of the input image using some Fourier analysis, and the result are worse, okay? Okay, so in this case, with the image, the difference in angle, in the acquisition angle is slightly 10 degrees, we can say that CGAN is better. And then we go to another example. So in this case, this is another area, also in Japan. We have pre-event and post-event different acquisition condition, but you notice the angle is much larger, right? So 20, more than almost 20 degrees. So in this case, the CGAN doesn't work, right? But we found that the CCA GAN, especially when we use the modulation with the Fourier transform, it works much better. And you can see in the tables here, right? Using the modulation with the Fourier transform works better for areas, especially this area when the difference between the off-nadir angle is very large. So this is the last slide. So this is our findings here. So when the difference between the incident angle or the off-nadir angle between pre and post is smaller, simple CGAN works. So we can translate the pre-event to the same incident angle of the post-event and do some simple change analysis, and we can get nice results. However, when the incident angle is larger, more than 15 or 10 degrees here, CGAN will not work. So there is much changes for the normal CGAN to translate or to understand, to learn from those things. So in that case, the CCA architecture, especially when we do some pre-processing, some modulation with the Fourier transform, it gives better results. So that is our finding. So for larger difference angle, much complex architecture is needed, and for smaller, probably CGAN, we are good with CGAN. Of course, we haven't analyzed the whole spectrum of difference. There are major differences. We only could get data that the larger difference 25 degrees or so. So there is more study to do in this part. Okay, this is my last slide. Thank you.
Next talk is by Omid.
Okay, hello again, everyone. And this is another work for landslide detection. Actually, like last minutes, I heard that I should present instead of my co-author who is in Canada and based on time. So anyway, this is a work from my side. From IARAI and Jojic INRS Quebec, Canada. The paper is going again for landslide detection, but here what we focus on that it is like model-centric and data-centric deep learning approaches for landslide detection. I'm also very happy, like earlier in the morning, we had like some AI solutions for landslide detection that some of them focus more on the first part of model-centric and some of them focus on data-centric. So yeah, I was really happy that what I'm thinking also happened in the real scientific world. So since 2019, that's the first very simple convolutional neural network I designed for landslide detection. So far, there are a lot of models designed for this task, and some of them are really common, like UNet that we use also as baseline for the competition. So I want just to say that they are looking really successful in this task. So model-centric, whereas data-centric. As I said, in some studies, we are going to work more on our model and make it more complex and complex to increase our accuracy for landslide detection. Whereas also sometimes we can work on like our data. Very simple example is data augmentation. But what we did in this study, just let me start from the study areas. It's again Hokkaido in Japan, and the same study area is divided to training site and site for testing the model. What we used was again unit, and in each step we make it more complex. Like we add like residual learning and RES unit, and then we also add attention mechanism for landslide detection. So now we have here also residual learning unit and attention mechanism. But in the data-centric, so we keep it very simple and we will work more on that. This part is also very simple, and what we did here, we simply add vegetation index NDVI to our previous data, and also one more. We used an unsupervised segmentation that we could control the size of the resulted segments objects, and we simply used the mean value of each object and added to the previous training and testing data in both on train and test images. So very simple. So it is very interesting that like using complex residual unit plus with attention mechanism, like we could like get the same result than when we just use simple unit, conventional units, but we just add two simple scenarios, NDVI and mean value of the objects that we created unsupervised. This is the whole thing that we present in this paper.
Final talk is going to be online.
Hello, everybody. I'm Valentin Barrea from the Joint Research Center, and I represent the work done with Martin Clavry on multimodal crop type classification, where we've used like a satellite image, farmer crop rotation, and local distribution inside the same model. So why we use crop rotation? It's a crop management technique that is used by the farmers. So the crop sequences are not random for like one parcel. So it allows to inject expert knowledge inside the modeling, the network. So for example, regarding the past crops, we are predicting the current crop. So we used multimodal features, so the crop types, 380 crop types over 12 years, we aggregated by an expert in 28 or 12 general classes. We used the Sentinel-2 Earth observation base feature, and finally the crop distribution. So it was like the 386 dimension vector representing the distribution of the crops in the surrounding of the parcel. So on 10 kilometer radius, so it allows to, because like in some places you don't have country, you have different crops than another place because of different reasons like climate or soil. So we focused on the data acquired over Netherlands. It was a total of around 600,000 parcels. So we model a problem as language modeling tasks. So the crop types were modeled as word, like in a language model. So for example, you predict the crop T+1, knowing the crop T from crop 1. So like a language model with the past words, you predict the next word. We model the Earth observation signals, so the satellite signals as acoustic signals. So we used a sliding window of size 30 days, and we made it move with a step of 15 days. And then on each like sliding windows, we use statistical functionals to temporarily aggregate the signals. So like the average mean, the median, the variance, the mean, the max, etc. And then we use the crop distribution, which act like a speaker-specific vocabulary. So in green, you can see like 10 crops of interest. In red, the grassland, which is the majority crop, and in blue, all the other crops that were merged into the class other crops for the 12 class settings. So those are like 28 crops. So we use like the hierarchical LSTM. So we have like different LSTM models. So the first one here, the green one, is acting at the year level for the remote sensing. So giving a representation at the year level for remote sensing. So it's a bidirectional LSTM with attention, and it allows to obtain one vector that represents the dynamics of the signals over the year. We fuse that with the embedding of the crop here using concatenation and multi-layer perceptron. And then this new vector was fed into a new LSTM. It was not bidirectional this time. Then the orange LSTM produced like a multimodal vector of the crop and the remote sensing that were also concatenate and fuse with the distribution of the year in order to find the crop distribution, in order to find the crop of the year too. So you can use the remote sensing of the current year, the crop of the past year, distribution of the past year, and you obtain the crop of the current year, even though you don't know anything about this year end. So we used like 2019 as development set and 2020 as test set. Here in the table of the results, you can see different models, modality, and class granularity. What is interesting is we compare to state-of-the-art models, so LSTM that takes the year independently. We can see like the results are far better for all the settings. We can see also that adding more modalities helps greatly, and also the type of the model. So LSTM MM or hierarchical bidirectional LSTM also helps. So it's not only the modality, it's also like the modeling. Finally, we use the data augmentation technique in order to do some in-season classification. So the model was trained over the whole year, so it was good at the end of the year to predict the crop. But sometimes it's interesting to predict during the season. So we used the data augmentation technique. We random cropped the time series of each satellite signals, and it helped to improve the robustness of the model. So as you can see, the blue performances in time are far better than the normal one that doesn't use data augmentation, the green one. The red is the crop only model. So in the mid-April, the O model is better than the crop only model, and it can reach in mid-June something like 80%. So we studied the integration of crop rotation. It's like a multimodal language model, like an automatic audio speech recognition. We had a local information. It outperforms the state-of-the-art by a great margin. And we proposed this data augmentation by random cropping, and it helps greatly in yield season. Thanks for listening.